Hello everyone, my name is Yong Nguyen from University. Today I come to the conference with the research topic about a systematic review with supply, demands, and economic effectiveness of urine diverting technology and product. Because the objective of this research is more likely to focus on identify the effective factor influencing the supply and demand side of the urine diverting technology and product. And also, I'm going to summarize some performances of the urine diverting technology in terms of economic feasibility of such system. And then to achieve this objective, my research methodology is based on the systematic reviews. And after a wide variety of search in different databases, I finally identified 64 included articles in my research analysis. And then this section, the first, the above section is more focused on my results. Because I just have 3 minutes, so I can't go in detail for those. So I just direct you the position of the project. So I will come with the poster out for detailed information. And the last part in here, I will go through discussion with the research results and some adaptation theories to discuss some solution for the project of urine diverting technology to achieve the early stage of the adaptation. Yeah.
Thank you. Thank you. Less than 3 minutes. Okay, great. So we have next Niti Bhattarai from UTS.
Thank you, sir. Hi, my name is Niti Bhattarai, and I'm So I am conducting research in the field of geotechnical engineering, and today I'm presenting a brief outline of how we're planning to proceed with our research, because it's still in a planning process and we haven't really started our experiments yet. The basic motivation behind our project is to establish these closed landfill sites. These closed landfill sites which are often weak structurally and in order to develop any infrastructure above that, they require certain ground improvement techniques, where the traditional ground improvement techniques that we're employing mostly make use of high mechanical energy or energy intensive materials like cement, which again comes with its own environmental issues. So the idea here is to look into the alternative methods that can really provide comparable engineering results and at the same time reduce the environmental impacts. So we've come with a technique called biocementation, which basically harnesses the leverages the biochemical reactions within the soil subsurface and improves the soil properties, and it does so through a series of chemical reactions. So the first reaction is urea hydrolysis, where urea's enzyme is introduced to the system to hydrolyze the urea to ammonium and carbamate, and then upon the introduction of calcium ion, this carbamate will combine with the calcium and precipitate on the surface of the soil particle and also in between the particles, to sort of bind them or cement them together, hence the term biocement came from there. So you must be wondering, where does the urine comes into play, or how this urine can be a valuable resource in this technique. So we know this urea is a important ingredient in this technique, and also know that urea is a major constituent in urine. So through our research, we're trying to develop a method which can incorporate urine, which can facilitate urine, where the urine can facilitate the biocementation inside these landfill materials, so that these old landfill sites can be developed as a feasible construction ground for various infrastructural developments. And we're doing this through a series of activities. First, we'll collect the urine from our very own urine diversion system that's located at UTS Faculty of Engineering IT building. Since this urea has tendency to hydrolyze quickly, we then add calcium hydroxide to increase the pH and preserve the integrity of urea in urine. We'll then introduce that urine along with nutrient values like extract and ammonium chloride to the landfill sample. And after the enrichment, we'll then test the landfill sample for its various engineering behavior. So by doing this, we're trying to develop a concept that intersects circular economy, sustainability, as well as engineering advancements, and all together with using urine as a valuable resource. Thank you.
Next we have Ibrahim Al-Salabi.
Thanks, Cheryl. Good afternoon, everyone. Just presenting this on behalf of Juan from the Botanic Garden. I'll be talking about nutrient end use using potting experiments. So our research was based on testing Erbil, which is a urine-based fertilizer produced by UTS, on spearmint. The objective is basically to compare Erbil to a commercial fertilizer, then to study that with 3 different potting mixes. And that was conducted at the Royal Botanic Garden in Sydney, which is a few kilometers away from here, in the nursery area, which is a north-facing site with enclosed access, where it's away from the public. As I mentioned before, the experiment was a factorial 2x3, 3 potting mixes, and then 2 fertilizer treatments with 5 applications each. We've conducted that over 6 weeks period, and then we've collected data every week on stem length and the number of stalks, and at the end of the experiment we collected data on biomass. From the results, we found that one of the treatments, which is a commercial fertilizer combined with vermiculite, was the best performing compared to all the rest. The Erbil fertilizer, which are the first 3 groups, has shown some kind of homogeneous performance, whereas for the commercial one, we saw some peaks in that treatment, which we are still studying to see what's happened with that treatment. For the number of stalks, we had the best one with Erbil was the one with vermiculite as well, and the same for the commercial one. And then the worst performing combination was the Erbil plus peat and perlite potting mix. For the biomass, we got the same result with the CMV, which is the commercial fertilizer, and vermiculite with higher biomass. For this one, there's the UPP, which is the Erbil and peat and perlite. So our conclusions were that we have to do more investigation to see why that happened in that potting mix, and then what contributed to the peak results. And also we have encountered some challenges with fungi in some of the treatments that we are still investigating what happened in those treatments, especially with the wet weather in the botanic gardens. I would like to thank the Botanic Gardens, the NICE Hub, and the UTS for supporting this research. Thank you.
Thank you. Right on time. Next we have Catherine Sulubian from CSIRO, Agriculture and Food.
Hi everyone. This poster is to introduce a new collaboration that was formed back in around about May this year between CSIRO and Caitlin Burt's lab over at ANU, and it's exploring creating biomimetic membranes using aquaporins to separate ions from mixed wastewater solutions. So Caitlin's lab studies aquaporins, which are protein channels that are embedded in the membranes of cells, and we're focusing on the aquaporins in plants because they perform a lot of different roles to separate ions, cations and anions from solution. So the goal of the project, we're working with Caitlin's team and then John Lee G's membrane team in our manufacturing group down in Melbourne to isolate these proteins and embed them into membranes so that we can create membranes that can sequentially separate target ions from solutions. So the first one we're starting with is ammonium, and that's for a couple of different reasons. The first is obviously it's a high value nutrient and there's a desire to recapture it. But the second is that it's a really important ion for plants, and so there's been a lot of research about the aquaporins that can separate ammonium from solutions by plants, and also there's quite a lot of genetic resources out there. So Caitlin's team has identified 17 different aquaporin targets for transporting or separating ammonium from a solution. And we're now in the process of screening those for their ability to be reconstituted and made synthetically. And then Jean-Lee's team, our postdoc Shiva Nandala, will look at embedding those into membranes, and we'll be able to start testing the permeance and selectivity of those membranes. After we've succeeded there, speaking optimistically, we will then move on to other ions of importance, so phosphorus, and even looking at some of the metals that might be of interest to the mining industry. Thank you very much.
Thank you. 2 minutes, 15 seconds. Next we have Jade Jiang from UTS.
So good afternoon everyone, I'm Jade Jiang from UTS. So I'm gonna talk about the potential nutrient recovery and removal and recovery from a hybrid membrane bioreactor and membrane capacity deionization systems. So here's a schematic. Anyway, the first one, that's a schematic diagrams of the hybrid MBO MCDI setup and the operation process. So in the substrate urine was initially stabilized through membrane bioreactors to convert volatile ammonia into a more stable form like nitrate and ammonia. Then after that, we feed the MBO permeate to the membrane capacity deionization systems. It's gonna go like 7 continuous absorption and desorption batch mode to produce the concentrated urine fertilizers. So the image on the left bottom, that's TDS variations in the treated and concentrated solutions on the 3 different voltage among 7 consecutive cycles. So as you can see, like the high voltage applied can resulted in a better TDS removal performance. And here, that's these two figures shows ion removal and recovery efficiencies. So similar to the TDS removal performance, like we noticed, like the low voltage resulted in a lower removal and recovery efficiencies of both cations and anions. And the performance can be significantly improved as you increase, like after you apply the high voltage and the high reverse voltage on the absorption and desorption process. So here's the energy consumptions for removal and recovery of ammonia and nitrite. We can see the energy demand for removal of ammonia was between 3 to 11.25 kilowatt hours per kilogram of ammonia, and that energy consumption was between 4 to 450 kilowatt hours per kilogram of the nitrate. So the energy required for absorption and desorption can even further reduced by harvesting the energy during the desorption stage. Then in conclusion, this hybrid NBR-MCDI system can effectively remove recovery nutrient and produce the urine-based fertilizer. Thank you.
Thank you. Next, we have Chen Wang from UTS.
Good afternoon, everyone. My name is Chen Wang. Actually, my today's topic is not very closely with nutrient recovery, but my previous work I mainly focused on the membrane fabrication and modification. But my current work is about the lithium recovery from seawater. So today's topic is about the graphene oxide-based layer-by-layer membrane for the nanofiltration application. So we know the commonly used nanofiltration membranes are thin film nanocomposite membrane, TFC membrane. The most commonly used method for the TFC membrane fabrication is the interfacial polymerization (IP). But in the IP process, we need to use organic solvent, which will bring the environmental waste pollution. So compared to the IP, the layer-by-layer assembly is more environmentally friendly method because we don't need to use organic solvent. In this study, we use the inkjet printing technique for the layer-by-layer nanofiltration membrane fabrication. Compared to the traditional deep coating or spring coating layer-by-layer method, the inkjet printing technique has some advantages. For example, the very easy and fast procedure, and also use minimum chemical consumption. And we can also control the chemical deposition on the membrane surface. So in this study, we use a homemade new PKE substrate as a support membrane, and we use the inkjet printing to print the active layer. So the PI is used as the positive ink, and gel is used as negative ink. We did the SEM to see the membrane surface and cross-section morphologies, and also we did the FPI, XPIs to confirm the printing of the PA and GO, and also the cross-linking reactions between the PA and GO and GA. Also, we tested the membrane performance in terms of different bilayer numbers and also the different PA and GO concentrations. And we also did the desalination performance test and long-term filtration test. Also, if you are interested in this study, you can see we can discuss more detailed information in the next room. Thank you.
Thank you. Next, we have Andrea Melinda from UTS.
Hello everybody, my name is Andrea from UTS. Again, it's a slightly different topic from what you've heard, I think, during the day. I'm going to introduce my poster, which also you find next door. So I have to introduce this topic a little bit, and I want to say that prior to the Industrial Revolutions, our ancestors for centuries had to rely on horsepower, muscle power as energy sources. Now, for decades, our society instead has relied on cheap and abundant fossil feedstocks such as oil to foster progress and technology as we know today. As Nobel Prize awardee Richard Smalley said in 2004, energy is the most critical factor that impacts prosperity in our society. But whereas we have relied for decades on cheap oil, right now we have hit a wall. And so the climate emergency, the need for new sustainable models, economic models, now have shifted our attention towards more sustainable sources of energy to be applied to a broad range of technologies. And in this scenario, the water energy nexus actually would play a key role to achieve our sustainability goals. And in my case, my aim here is to develop technologies for the water treatment sector that are more cost and energy efficient to build the next generation of resilient wastewater treatment technologies. And in my poster, I'm dealing with an urgent threat in water treatment, which is actually caused by anthropogenic activities that have generated some emerging contaminants. Some contaminants that our nature doesn't know and doesn't know how to degrade naturally. So our design our idea is to design actually a solution, a technological solution, combining both filtration and degradation of organic pollutants on a single unit. And this is done by actually designing membrane catalytic reactors. So what we did was depositing an ultra-thin layer of catalytic materials that can actually integrate reactivity with selectivity on a single unit. But the key piece in this jigsaw puzzle is actually the green one. These catalytic membrane reactors can be powered and driven by renewable energy to actually improve the energy efficiency and possibly achieve carbon neutrality. Now, in my poster, I'll also be dealing with, okay, what is hindering right now the scaling up of these technologies, because there are technologies in the market available, at least at pilot scale, and I'll be dealing with this in my poster. And also I'll be presenting some of our recent advances in this regard, consisting of mostly of photoelectrocatalytic membrane reactors. So if you want to discuss more, if you're interested more in the topic, please come and see me next door. Thank you.
Next is Hao Lui from UTS.
Good afternoon, everyone. I'm Hao Liu from UTS. My topic is enhanced strategy for phosphate recovery from urine by magnesium galvanic process. What is magnesium galvanic process? It is very simple. Just one magnesium plate and one stainless steel plate and connecting with a wire. And if put it in a solution, you can continuously releasing magnesium ion. And magnesium ion in urine can form struvite to recover phosphate. And based on there are many ions in urine, like ammonium chloride carbonate. So there are different passive films formed on the magnesium plate. And based on our results, we found that in ammonium chloride solution, the magnesium ion releasing rate is best. So we add in the hydrogen chloride into real hydrolyzed urine, and this is over 95% of phosphate can be recovered in a continuous floating rate. And this is our designed reactor for magnesium galvanic cells. inlet outlet, screw white outlet, and this is at the same time we can collecting hydrogen. And this is a video how it works. This screw white can precipitate on the bottom of reactor, and the hydrogen small bubble can come out into the top. And we also do the economic analysis for 1 cubic meter urine. We can the revenue is 14.68 RMB. It's equal to $3. That's all. Thank you.
Thank you very much. Is the last speaker here? No, isn't there one? Okay. So last speaker couldn't join us. Someone was planning to present, but I think he'll be in the poster display here. So thank you everyone for your nice presentation. So next we go to the display here, and then you can ask